about the linear transformations, the rotation, combination of linear transformations, and then another type of transformation is the inverse LT, which we should all accept this, right? So inverse LT, it is any linear transformation which transforms between this space from W to V space, and the T would be the opposite. So this would be the inverse linear transformation, and in this case, we know that if T is equivalent to a matrix A, then the T inverse is equivalent with an inverse matrix A inverse. Then
that means that the determinant of E is always different from 0, right?
Let's think about it. So, in order to have an inverse linear transformation, yes, I believe this should be the case. Yes, the determinant, because it has to exist. Yeah. Yes, I think that's the answer. Let's see an example. Let's assume that we have a linear transformation represented as T x, y, z, and this is equal to the matrix that we obtained in the previous session from 1, minus 1, 2, 1, 0, minus 3. And this one, we apply this on x, y, z. And we should not forget that this was the matrix A. Now, the question is, let's find what is T inverse, okay? This is the question. So how can we find the T inverse? We could, so given this as a question, we want to identify, this means that this question is equivalent to the following. And to find the A inverse, we follow the procedure which includes augmenting a matrix A with an identity matrix, following a series of linear elementary row operations. We should get here I, and here we should get A inverse. Okay, so we know how we move with this procedure, and we could cover a couple of steps. So we have here 1, 1, 1, 1 minus 1, 0, 1, 2, minus 3, and what we could do is that we know that we want to make 0 these elements here, so we can just subtract from the second row, we can subtract, and from the third row, we subtract the first one, because we can easily make these two equal to 0. So we get here 1, 1, 1, 1, 0, 0, nothing changing here. Then here we get 0, minus 2, minus 1, minus 1, 1, 0. Then the rest, the third row, this is 0, 1, minus 4, 0, minus 1, this is minus 1, 0, 1. So this is the first step, and this is the separate, this is minus 4. Then the next step, we can divide by 2 all the second row. So if we divide the second row by 2, we get here 0. Actually, we can also divide this one by minus 2. So if we divide by minus 2, this is going to be equal to 1. This is 0.5. Here we get 0.5 minus 0.5. And 0. Then the next step is that we can subtract from the third row, we can subtract the second one. So this would mean that here we have 0, 1 minus 1, 0, minus 4, minus 0.5, this is 3.5. I believe this is correct. And then we have minus, wait a second, here we have minus 1, minus 0.5, this is minus 1.5, 0, minus 0, this is 0.5.
Professor, can you adjust the camera a little bit down?
Oh, okay. Yes, that's a good point. We should.
Thank you.
Thank you, you're welcome. So we get here 0.5, and this is 1 minus 0, this is 1. The first row we are not changing. Then what we do next is that we can multiply by 2 over 7. So if we multiply here 2 over 7, we get here 1. And once we have these ones here, this is the first step of trying to obtain an identity matrix from what it was initially equal to A. So if we follow all of these steps, we obtain the following matrix. So A inverse. Now I believe the camera. No, it's good. So the A inverse is going to be equal to 1 over 9, 3, 3, 3. 5 minus 4 minus 1, 5 minus 4 minus 1, 1, 1.
Oh, Professor, you have to move the camera up again.
Okay, you're missing something. Okay. So the A inverse, this is the matrix that we want to find. Now that we know this A inverse, it should be easier for us to identify what is this inverse linear transformation T that we were asking in the first place right here. So in this case, we have to determine, we say that this T inverse, if we apply this on a vector u, v, w, this would be equal to 1 over 9 times the same matrix 3, 3, 3, 5 minus 4 minus 1, 1, 1 minus 2 times u, v, w. This will all be equal to this is u over 3 plus 5v over 9 plus w over 9 plus w over 9. The second row, it's again u over 3 minus 4v over 9 plus w over 9, and then we get u over 3 minus v over 9 minus 2w over 9. So apparently this is the T inverse, or the inverse linear transformation that we were asking. Okay, I hope this is clear. Now we can cover, so this is how we determine the inverse LTs. Now the next thing that we can talk about is the following. We can, for any matrix A, we know that we have defined the range, the null space, and many other spaces which are related to the matrix. These sets or subsets, we can define them also for the linear transformations. So we can talk here about the range and the null space of a linear transformation. Now, in the previous hour, we also we just briefly mentioned the idea of the null space in a linear transformation. And here we can say that, so at least we know the formal definition of what a range is, but let's write this again. So the range of any linear transformation T is equal to T applying the linear transformation V on all the vectors which are in vector V's, right? So this is the range. We apply whatever the transformation is on all of the vectors, which in this case would be x, y, z. And these are such that all these vectors here this is the best way I can denote this one, are elements of the vector space V. So, and at the same time, we can say that this is equal or equivalent with the range of a matrix A. Okay, assuming that matrix A, it is equivalent to the operation which is done by the T. Now, similarly, the null space of any linear transformation NT, we're going to give the definition, but this is going to be equal to the null space of A at the same time, right? Now, you have very good knowledge of how to find the null space of any matrix A. Now, this should be equal. Now, let's see, let's look at the formal definition. The null space of T is all the vectors which are in the vector space V, okay, such that TV is equal to what? Okay, so this is the null space of T, and we know that this definition, it also works for the null space of A. Then, let's see, null space. Now, null space here, in this domain, we can also call this one the kernel. Kernel of A is in fact also denoted as the null space of A, and assuming, so this is the range of A, and this range of A, it's what subspace is this is the subspace of W. Okay, and the kernel or the null space is the subspace of V, assuming that the linear transformation is a transformation from V to W, at least the notation that we have used today. So again, we're talking about null space, kernel space, or kernel of the matrix A, kernel of the linear transformation, and the range. So I believe that the most intuitive approach, which can be useful and which can help all of us when we think about the range and the null space, especially for the range, is to consider the range as a linear combination of the columns of A. I know that most of you already is clear to you that this is how is the best way to try to perceive it. Now, okay, so we have also the rank nullity theorem. This rank nullity theorem that we have seen for the matrices, it also stands for linear transformations. Okay, and what this states, it states that the rank of T, rank of any linear transformation T, plus the nullity of T, this would be equal to the dimension of V. Okay, so this is something that we already know, and the nullity rank dimension. Okay. Okay, so let's come to the best topic that we are going to discuss today, which is the coordinate change. And so, regarding the coordinate change, let's assume that we have initially, this is not good, let's assume that we have standard basis. Standard basis, it is defined as having the basis described by 1, 0, 0, 0, 1, 0, and 0, 0, 1. This is a standard basis, but one can come up with a different basis actually we have an infinite number of possible combinations for a specific basis. Let's write down one of them, which is 1, 2, minus 1, 2, minus 1, 4, and 3, 2, 1. So this is a different basis. The only thing that we may need to make sure that this is really a basis is try to determine the determinant of this 3 by 3 matrix. If we check it, the determinant is equal to 4, so it's a good one. But let's not forget, this is called, let's consider this one, basis B1, okay? And let this be the standard basis. Okay, and before we do into the examples, we can first provide the formal definition of the coordinate change. Now, if VI is basis B for Rn, okay, this means that any vector x, okay, is equal to alpha I times Vi. Let me denote it like this. So again, what will be the basis here? The first column is V1, the second column is V2, the third column is V3. Okay, so this is what we need here. And then the coordinates here, x, according to basis B, are equal to alpha 1, alpha 2, alpha n. Okay, so these are called the coordinate vector. This is coordinate vector with respect to basis B, with respect to basis B. Now, what we're going to often see will be the following. We are going to have a vector which adhere in this domain, or according to this basis, we're going to report the coordinates. Then we may want to see what is a projection of the same vector represented by some coordinate vector here. How does it look like in this new basis? Okay, so we want to conduct base change regularly. Now, let's assume, now if we look carefully at this expression here, we can write this one as follows. So this x, which is n by 1, okay, this is in fact equal to vector v1, vector v2, and these are columns, okay, and this is vector vn multiplied by alpha 1, alpha 2, and alpha n, okay, because we know that. So now let me put here a v2. How should a v2 look like? Well, let's pick this one, 2 minus 1, 4. 2 minus 1, 4. Just as a reminder of how these things are going to look like. And we can pick up some other vector in between, assuming that we have, let's say also a 0 again. This can look like 3 minus 3, 0, 1, whatever. So I'm just reporting these as examples. And whenever we multiply these with alpha 1, alpha 2, alpha n, this is in principle the summation of alpha I times Vi. And this is in fact equal to, let me write it here, alpha 1 V1 plus alpha 2 V2 plus alpha n Vn. So this is how a certain vector can be represented in some specific vector where the basis is not E1, E2, E3, or possibly E4, but it's something different. Okay, and then what we can observe from here is the following. Now, allow me to erase this part, because this is something that we clearly notice. But let's have a look for a moment of what this is. Now, this in itself is a vector, okay? So how do we denote this vector? This vector, we denote it like this. This is x, projection of x on the basis B, right? And this one, the matrix, which is composed in its columns by the basis vectors, let's denote this one as P, matrix P, okay? And what we observe here is that this vector x is equal to vector P, matrix P, times x according to basis B, okay? Now, we can also write the same as P1. So we can have another basis, right? Multiplied by the coordinates of x according to B1. So, because the same vector x, it can be written as different basis vectors or different matrices times the projection of this vector onto B1. Again, we can write here P2 times the projection of x onto B2 and so on. Now, but let's leave this one for a moment like this. In principle, we should know that this x here, this is according to the standard basis. Now, it is best if we represent this one with an example, because everything it will become clear. So let's assume, in an example, that we have a basis which looks like this: 1, 2, minus 1, and they're going to look like a matrix, but as a reminder, we have to think of these as columns. So in this example, we assume that we have this basis and the coordinate vector given that the projection of this vector x according to basis, let me call this one here basis B1 here, okay? Let this be equal to what is given here, 4, 1 minus 5. 4, 1 minus 5. Given this, the question is find x. This is the question. Okay, so how are we going to solve this? Apparently, yes?
We know that the coordinates, the components of the vector xbi are the coefficients that we should add before the columns of the matrix to find the vector. Because the vector x can be expressed as a linear product of the columns of the matrix.
That's true. So then we can do here 4 times 1, 2 minus 1, right? Sorry, this is over. This is. So then we do 1 plus 1 times 2 minus 1, 4. 2 minus 1, 4. Then minus 5 times what? 3 to 1. And by the way, since we are in this basis, let's write down how this vector looks like in this basis. So it is 4, 1 minus 5. 4, 1 minus 5. Okay? And we want to find how does this vector look like in this domain. And this is what we are doing now. So what is this equal to? We have 4 plus 2, 6, minus 15.
Minus 9.
Then?
Minus 3, minus 5.
Minus 3, minus 5. So this is according to the standard basis. We get minus 9, minus 3, minus 5. Minus 5, yes. So we found it. Now, how did we find it? We noticed that this one was equal to what? This one is equal to the so this was basis B, but let me write this one as a matrix P1, right, times this vector here, 4, 1, minus 5, 4, sorry. And now, and apparently this was equal to our x, whatever. Now, if we don't put any notation here, this means that this is according to the standard basis. Now, we can ask another question. We can ask, and these two are linked together. So, what did we do here? This was standard basis. We went this way with the matrix P1. Okay. Let's see if you can see it. You can still see it, yeah. Now, we can ask another question. We can say, if we are given a vector in the standard basis, which is equal to 5, 7, minus 3, how does this vector look like in the basis B1? So, these two...
We use P1 inverse.
That's correct. This is what we have to do, okay? So, if we are given a vector in this domain, we can move backwards with P1 inverse, okay? So, if we try to identify, so now I believe that this formal definition, which might look somewhat confusing, once we see this example, it should become a little more clear. So, the most essential part here on this part of the board is this, okay? And let me take now, first we need to identify what is the P inverse, and the P inverse, this is equal to 1 over 4 times minus 9, minus 4, 7, 10, 4, minus 6, 7, 4, minus 5, okay? So this is the P inverse. Let's multiply this one with the 5, 7, minus 3. So if we multiply these two together, what we obtain is 1 minus 1, 2. And then it looks like this is going to be 1 minus 1, 2. And these two are linked together. So we move this way by applying this vector, the P1 inverse. Okay? Now, this was the basis change. Now, what we can do here is that we can construct also another basis that which would be basis B2. Okay? And in this basis B2, maybe you can help me. Let me try to identify if I have any, wait a second, any inverse matrix. So what we can do is the following, in fact. That's we can come up with another basis, 1 minus 1, 0, 0, 1, 0, 3 minus 2, 5. So this is another basis, B2, and if we want to determine, let's think for a moment. So this is the standard basis. Let's say that we have a vector which looks here like 1, minus 1, 3. Now, this one is a vector which are the coordinates of a vector in basis B2. Now, we may want to see how, what is this vector in this other domain. How can we do it? Any idea how we can do it?
We need choose to transform it to standard basis first, or we also may use the equations Pn times the vector x in basis n is equal to Pm times the x to the another basis.
Okay, so now let's assume that this matrix that we see here, it's composed by the same vectors. It's not difficult. This is P2. Okay, so this is P2, and let's see how does actually how do we denote this one? This is denoted as vector x in basis P2. Let's see how does that one look in the standard basis. We have here 1, -1, 3, and according to basis B2, we multiply it with the matrix which we have provided, which is composed of these vectors 0, 0, 1, 0, and then we have 3 minus 2, 5, 3 minus 2, 5. So let's see what we get. 1 plus 3 plus 9, 10. -1, -1, -2, -2, -6, -8, and then we get here 15. Okay, so here we got a vector which is 10, 8, 10 minus 8, 15, and we are in this domain. Now let me write it here. 10 minus 8, 15. 10 minus 8, 15. So we found it. This is how it looks like in the standard basis. What about in V1 basis? What is this vector in this basis? We need to
use the inverse matrix we found earlier.
with this one, right?
Yes.
Yes, that's true.
It's 1 over 4 times -9 minus 4, 7.
Yes, so what we do is that we just multiply here again with these numbers. 1 over 4 -9, 10, 7. Sorry, this is a little congested. -4, 4, 4, 7 minus 6 minus 5, 7 minus 6 minus 5. And it looks like we could, so let's see actually what we get. Now you are writing this on your, we can calculate. I don't know the answers right away, but you might be a little faster than me. You can calculate this one, so let's separate it like this because it doesn't look the best way possible. But it looks like we can find some numbers here, A, B, C, which are according to basis B2. No, wait a second, B1. This would be the projection according to basis B1 because we progressed with P1 inverse. So it looks like for any vector x in a basis B1, this was equal to what? This was equal to P1 inverse times P2 times the projection of the vector x in P2. Okay? So, if we keep, so it looks like we can keep the standard basis in the center. Now, what we mean in the center, we can use it as a very good reference point to transform from one basis to another. Okay? So here we have the central picture. Let's consider this one the central picture. And we can come up with a different basis. So another domain, we have a basis B3, right? If we have a basis B3, how can we move to the standard basis? We always move with the matrix P3, right? The matrices which are composed of the basis, they all send you to the standard basis. Again, we can have another basis, let's give it here, B4, and this B4, we need to know what is the basis for B4. We will be given a triplet of columns, of column vectors, and we know that we go to the standard basis using P4, okay? And similarly, we come backwards with P4 inverse. And here, we come back down with P3 inverse. So So from here, from this schema here, it is very easy for all of us to determine what would be the projection of this vector x according to basis B4, right? So we just do the following. Where are we? We have this vector x, or let's do it in basis B3, or let's say in B3. If we have a vector x according to basis B3, we know we need to go to the standard basis. How do we do it? We multiply with P3. That's easy. And then where do we want to go from the standard basis? If we want to go to B4, we multiply with P4 inverse, and we get what? This is x, the projection of x on basis B4, okay? Or similarly, if we want to see the projection of vector x according to basis B1, what is this equal to? This would be P1 inverse times P3 times x in basis B3. Or let's say we want to find the relationship of, or how, give me a second. So we want to find how we go from basis, I don't know, now we are exaggerating this a little bit, we want to go from basis B7, and how is the relation between a vector in basis B7 and B8. So what we do is that
P7 minus 1 times P8 times, yes.
That's correct, that's right. So, I mean, so apparently we learned that by using the standard basis as a bridge between different bases, this is how we do it, okay? And this is a very elegant way, and one of the most useful techniques that we use in linear algebra. What is left from the most beautiful part of linear algebra is the fact that we can, so it looks like it's a straightforward technique how to jump from one basis to another. Now, the biggest question for all of us that we're going to come very, very close is the following. Which one is the best basis? Is it B1, B2, B3, B4, or some other basis? This is the next most important question.
Probably the one that has most zeros on it.
That was a good answer, but probably it's not the best. Find the best basis. This is the next big question. Okay.
The standard basis, because if we multiply a vector with standard basis, we get the vector.
Well, you know, but the thing is that this is find the best basis. The first option you are saying it's the standard basis. Okay. We have another answer, so this is a good option. So we can put this could be an option. But the general question is that the best basis or the most because let's also think about this one. If we have a problem or a data set, let me say it this way. So let's assume that I have a problem which I can represent it by a matrix A1, okay, a data set. And then I have another problem which we have a data set which is represented by a matrix A2. But they are different matrices, they are not equal. If the best basis is the standard basis, okay, that means that we always go, it looks like the basis or the best basis, if this was the correct answer, it would be independent of what our data set is, okay? So I'm putting the problem this way. Think about this one. You have A1, A2, that's good. You're trying to look at the best basis. If your answer is true, that means that independently of what the problem is, independently of what the data set is, the best basis is the same one. This does not look like the best answer, okay? Because the best basis should be depending somehow, to some degree, with the form or the combination of how the data is provided to us, okay? Or let's call it this way. Now we have a generalized version. We call this linear transformation. So not all the linear transformations can find the best representation in what? In the standard basis. And partially, the correct answer is the following. the best basis depends on AI. Okay, I'm saying AI. So if we have A1, it should be one best basis for A1. If we have A2, we have another best basis for A2, and so on. Okay. So if we say it like this, if it's going to depend on A1, this part becomes questionable. Okay, or maybe not 100% true. And the next journey of ours is we have to find this best basis. And for this, we're going to very soon talk about the eigenvectors. I know that we have not started eigenvectors yet, I know this, but this is a very good point. Since we are discussing about different bases, I have to we have to discuss together that the best basis is something which is going to be created or formed or formulated from the eigenvectors of a specific matrix. Okay. Now here we, I was going to say something else, but we are not there yet because we have to start with the eigenvalue equation and the eigenvectors. Okay, do we have any question?
No.
Okay. I believe, let me see the time. Okay. The time is almost over. So if you have no more questions, we could bring this to an end for today.